The Empty Sky. A Historical Drama of Innovation and War. Part 1, The Unsolvable Equation. Chapter 1, December 7, 1941, Pearl Harbor. The morning air tasted like salt and failure. Major Thomas Tex Riley stood beside his 90mm anti-aircraft gun, watching the last of the Japanese bombers disappear into the cloudless Hawaiian sky. His hands still trembled, not from fear, but from the impotent rage of a man who had fired 47 rounds at aircraft he could see, track, and predict, only to watch every single one of them sail harmlessly past their targets. The problem wasn't courage. The problem was mathematics. Reload. Riley barked, though the attack was over. His crew moved like automatons, their faces slack with exhaustion and something worse, the dawning realization that their weapons were obsolete. Around them, Pearl Harbor burned. Black smoke rose in thick columns from the Arizona, the Oklahoma, the California. The air stank of burning oil and something else Riley tried not to identify. Corporal Henderson, the gun's pointer, sat with his head in his hands. "I had them, sir. I swear to God, I had them in my sights." Riley knew Henderson was right. The corporal was the best pointer in the battalion, a Kentucky boy who could hit running deer at 300 yards. But hitting a deer and hitting an aircraft moving at 200 miles per hour at 12,000 feet were two entirely different propositions. The mathematics were brutal. By the time a shell reached the altitude where an enemy aircraft had been, the aircraft had moved. Leading the target, calculating where the aircraft would be in the 15 to 20 seconds it took for the shell to reach altitude, required simultaneous calculations of aircraft speed, direction, rate of climb or descent, wind speed and direction at multiple altitudes, the ballistic trajectory of the shell itself, and the rotation of the Earth beneath it all. Human beings simply could not calculate that fast. Riley had done the arithmetic himself 100 times during training exercises. Even the best gun crews, working with the finest mechanical predictors and optical range finders, achieved hit rates of perhaps 2 or 3% against maneuvering targets. Against the Japanese bombers this morning, his crew's hit rate had been exactly 0%. "Sir," Henderson said, his voice hollow. "What do we do? How do we stop them next time?" Riley had no answer. He stared at the burning harbor and thought about the word leading, that simple concept that had defeated the finest gunners in the United States Army. You had to shoot not at where the target was, but where it would be. In training, with predictable drone aircraft flying straight courses, they could sometimes manage it. In combat, with real pilots taking evasive action, it was impossible. Somewhere in Washington, Riley knew, there were engineers and scientists working on this problem. There had to be. Because if they couldn't solve it, if American gunners remained unable to defend against aerial attack, then every city, every ship, every soldier in this war was vulnerable. The sun climbed higher. The fires burned. And Riley made himself memorize this feeling, this impotent fury, so that he would never forget what it cost to aim at yesterday's ghost while the enemy flew on into tomorrow. Chapter 2, Applied Physics Laboratory, Silver Spring, Maryland, January 1942. Dr. Eleanor Vance stood before a blackboard covered in differential equations and stared at what should have been impossible. The requirements were written in neat chalk on the left side of the board. 1. Device must withstand 20,000 G-forces during firing. 2. Must fit inside a 5-inch artillery shell, 5-inch diameter, 24 length. 3. Must contain radio transmitter, receiver, vacuum tubes, battery, detonator mechanism. 4. Must function reliably after exposure to -40 degrees Fahrenheit to +140 degrees Fahrenheit, salt spray, vibration, storage for 6 months. 5. Must be producible at rate of 40,000 units per month. 6. Unit cost, less than $20. 7. Failure rate, less than 2%. Eleanor had been awake for 36 hours. She was 30 years old, had a doctorate in physics from MIT, and had spent the last 5 years doing respectable research on radio wave propagation. That peaceful life had ended 6 weeks ago when Dr. Merle Tuve, director of the Applied Physics Laboratory, had called her into his office and handed her a file marked top secret. "We need you to build a radio that can survive being shot out of a cannon," Tuve had said without preamble. "Then we need you to manufacture 1 million of them." Eleanor had laughed. Then she had opened the file and stopped laughing. The concept was elegant. A miniature radio transmitter in the nose of an artillery shell would emit radio waves as the shell flew toward its target. When those waves struck an aircraft, they would reflect back to a receiver in the same shell. As the shell approached the aircraft, the frequency of the reflected waves would increase due to the Doppler effect, the same principle that made a train whistle sound higher-pitched as it approached. When that frequency reached a critical threshold, indicating the shell was within lethal range, the fuse would trigger the detonator and explode the shell. No need to score a direct hit. No need for a timer fuse that might explode too early or too late. The shell would detonate itself when it sensed it was close enough to kill. The problem was everything else. Eleanor turned from the blackboard to her workbench, where the current prototype lay in pieces. She picked up one of the vacuum tubes, RCA's new miniature design, called a proximity fuse tube, though everyone in the lab had taken to calling the entire device by that name. The tube was smaller than her pinky finger and more fragile than a Christmas ornament. "You planning to sleep ever again?" Eleanor looked up to find Dr. James Barker standing in the doorway. Barker was the mechanical engineer assigned to her team, a rail-thin man of 45 who had designed farm equipment before the war and now designed death. "Sleep is for people who aren't trying to fit a radio transmitter inside a bullet," Eleanor said. "Artillery shell," Barker corrected automatically. He crossed to her workbench and picked up the fuse casing. "Any progress on the G-force problem?" This was the nightmare that haunted Eleanor's dreams. When a 5-inch shell was fired from a naval gun, the acceleration from 0 to 2,000 feet per second happened in approximately 0.003 of a second. The forces involved were equivalent to dropping a car from a 10-story building and expecting the radio inside to keep playing. "I've been thinking about it backwards," Eleanor said. She grabbed a piece of chalk and began sketching on a clear section of blackboard. "Every engineer approaches this as a shock absorption problem. How do we cushion the components so they survive the initial acceleration?" "Because that's what it is," Barker said. "No." Eleanor's chalk scratched faster. "It's a resonance problem. We can't stop the shock, we have to design components that vibrate at frequencies that won't tear themselves apart. The vacuum tubes, the battery connections, even the solder joints, they all need to be tuned like violin strings." Barker stared at the sketch. "That's actually brilliant. Or completely insane. Possibly both. It's the only way to meet requirement number 5, Eleanor said. She tapped the production number on the board. 40,000 units per month means we need assembly line techniques. We can't have skilled craftsmen hand-adjusting shock absorbers on every unit. The design has to be inherently robust or it's worthless." She didn't mention the other pressure, the one that kept her working through the night. Her brother David was a gunner on the destroyer USS Mahan, somewhere in the Pacific. Every day the Navy couldn't defend itself against Japanese dive bombers was a day her brother might die because Eleanor Vance hadn't been clever enough to miniaturize a radio. "When's the next test?" Barker asked. "Friday. Aberdeen Proving Ground. They're going to fire 20 prototypes out of a 5-inch gun and see how many still transmit after impact. What's your prediction?" Eleanor looked at the delicate tubes on her workbench. "If we're lucky? 3. If we're not? 0. Barker winced. "Tuve's going to have our heads. Tuve can get in line behind the Japanese." Eleanor picked up another tube and held it to the light. Inside the glass envelope, the tiny filament gleamed like a thread of captured starlight. Somewhere in that fragile architecture was the answer. She just had to find it before time ran out. The clock on the wall read 2:47 a.m. Eleanor turned back to her equations and kept working. Chapter 3, The War Department, Washington, D.C., February 1942. The conference room was thick with cigarette smoke and the metallic taste of barely controlled panic. Brigadier General Harold Preston stood at the head of the long table, looking at the faces of the men who were supposed to win this war, and saw only doubt. To his left sat the artillery specialists, the anti-aircraft experts who had spent 20 years perfecting systems that Pearl Harbor had rendered obsolete in 20 minutes. To his right sat the scientists and engineers, academic men suddenly thrust into the machinery of war and terrified they would fail. "Gentlemen," Preston said, "we have a problem that requires a miracle. I need you to tell me if miracles are possible." He nodded to his aide, who pulled down a large chart showing aircraft shoot-down rates. The numbers were damning. Current anti-aircraft effectiveness stood at approximately 2,500 rounds fired per kill. In the Battle of Britain, British anti-aircraft guns had fired over 20,000 rounds to bring down a single German bomber. "The mathematics are simple," Preston continued. "If we maintain current effectiveness rates, we will run out of ammunition before we run out of enemy aircraft. We need to increase our hit probability by a factor of 5. Minimum. And we need it in 12 months. A colonel from Army Ordnance raised his hand. "General, with respect, what you're asking for isn't an improvement, it's a revolution. To increase hit probability 5-fold would require simultaneous advances in targeting, fire control, and ammunition. That's 3 separate miracles, not one. Then deliver 3 miracles, Colonel." Preston's voice was ice. "Because the alternative is losing this war." He turned to a tall, angular man sitting halfway down the table. "Dr. Bush, what can your people give me?" Vannevar Bush, director of the Office of Scientific Research and Development, stood slowly. He was 62 years old and looked older, worn down by the weight of every weapons project the United States was pursuing simultaneously. But his eyes were sharp. "We have 3 projects that might converge into a solution," Bush said. He gestured to the men around him. "Dr. Tuve's team at Applied Physics Laboratory is developing a proximity fuse, a radio-equipped shell that detonates itself when near a target. Bell Laboratories has designed a fire control computer called the M9 Director that can calculate firing solutions faster than any mechanical predictor. And MIT's Radiation Laboratory has developed a microwave radar called the SCR-584 that can track aircraft with unprecedented accuracy." 3 separate systems, the colonel objected. 3 parts of one system, Bush countered. "The radar is the eyes, it sees the target's position, speed, and altitude. The M9 Director is the brain, it calculates where the target will be and where the gun must aim. The proximity fuse is the fist, it guarantees a kill even without a direct hit." Preston felt something stir in his chest. Not hope, not yet, but perhaps the possibility of hope. "Explain the director." A younger man stood, Charles Draper from MIT's Instrumentation Laboratory. "Sir, the M9 is an analog computer using mechanical gyroscopes, servomechanisms, and electrical circuits to solve the leading problem in real time. Feed it data from the SCR-584 radar, and it will compute the exact bearing and elevation the gun needs to hit a target up to 40,000 feet and 6 miles away. It updates these calculations 30 times per second. 30 times per second, Preston repeated. A human pointer could never. That's correct, sir. Human gunners can't keep up. The M9 has to drive the guns directly. The crew just loads and fires when the director tells them to. The room erupted. Artillery officers were shouting over each other, outraged at the suggestion that their trained gunners be replaced by a machine. Preston let them vent for 30 seconds, then slammed his palm on the table. Enough. I don't care about your pride. I care about results. He turned back to Draper. You're telling me your machine can solve in real time what currently takes a fire control team 3 minutes? Yes, sir. But there's a catch. Draper's expression was grim. The gun crew has to trust it completely. The M9 will order them to aim at empty sky, at where the target will be, not where it is. If the pointer tries to correct based on what he sees, he'll miss. The crew has to aim at the ghost and believe the ghost is real. Preston understood immediately why the artillery officers were angry. He was asking them to abandon 20 years of training and experience, to trust their lives and their mission to a black box full of gears and vacuum tubes. He was asking them to close their eyes and shoot blind. But he was also looking at numbers that showed the current system didn't work. How soon can you have a working prototype? He asked. 6 months for the M9, Draper said. The SCR-584 is already in limited production. But, he glanced at the elderly scientist beside him. Dr. Tuve stood. The proximity fuse is the bottleneck, General. We've demonstrated the concept, but we can't produce it in volume yet. Dr. Vance's team is working on reliability issues, and we're having difficulties with manufacturing tolerances. Difficulties you can overcome? Tuve hesitated. Ask me again in 3 months. Preston looked around the table at these exhausted, desperate, brilliant men. Gentlemen, you have your orders. I want weekly progress reports from each project. Dr. Bush, you will have whatever resources you need, money, materials, personnel. If someone tells you no, you send them to me. He paused, making eye contact with each man present. 2,500 rounds per kill is unacceptable. By this time next year, I want you to give me 500 rounds per kill. Better yet, give me 100. Give me a system so effective that a single battery can defend an entire city. Because if you can't. Preston didn't finish the sentence. He didn't need to. Everyone in the room knew what failure looked like. They had all seen the photographs from Pearl Harbor. As the meeting broke up, Preston caught Dr. Bush by the elbow. Vanavar, level with me. Can they actually do this? Bush looked at him for a long moment. Harold, I've been a scientist for 40 years. I've learned not to bet against human ingenuity. But I've also learned that some problems are harder than they appear. He pulled out his pipe and tapped it against his palm. Your 3 miracles, radar, computer, proximity fuse, each one alone would be worth a Nobel Prize. You're asking us to perfect all 3 and integrate them into a single weapon system in 12 months while fighting a world war. If we fail. We won't fail, Preston said. He said it with more certainty than he felt. We can't afford to. Bush nodded slowly and walked away, leaving Preston alone in the smoke-filled room, surrounded by charts showing impossible requirements and insufficient time. Outside the window, Washington, D.C. spread out in the February cold, millions of people depending on miracles they didn't know they needed, delivered by engineers they would never meet. Preston made himself look at those people and remember why failure was not an option. Part 2, The Secret War. Chapter 4, Aberdeen Proving Ground, Maryland, March 1942. The artillery shell emerged from the cannon at 2,000 feet per second. Eleanor stood 200 yards away behind a reinforced concrete bunker, watching through field glasses as the shell arced upward into the gray morning sky. Inside that 5-inch cylinder of steel was everything she had worked on for the past 2 months: miniature vacuum tubes, a radio transmitter no bigger than a cigarette pack, a battery the size of her thumb, all held together by solder joints she had formulated herself. The shell reached apogee and began its descent. Eleanor held her breath. At 500 feet, it exploded in a brilliant flash. But not from the impact fuse, from the radio proximity fuse. The VT fuse had survived the 20,000 G launch, transmitted its signal, received the echo from a target balloon, calculated the correct detonation point, and fired. Contact, shouted the range officer. Clean detonation at optimal burst height. Eleanor felt her knees wobble. Around her, the APL team was erupting in cheers, but she could barely hear them over the pounding of her own heart. 3 months ago, 0 fuses had survived firing. Today, 12 out of 15 had worked perfectly. Dr. Vance. She turned to find Dr. Tuve striding toward her, his normally stern face split by an enormous grin. 80% success rate. Eleanor, do you understand what you've done? It's still not 98%, she said, but she was smiling too. We need to celebrate, then we need to scale up production. Tuve grabbed her by the shoulders. The Navy is screaming for these. I just got off the phone with Admiral King's office. They want 50,000 units for the Pacific Fleet. 50,000. Eleanor's smile faded. Sir, we're hand-assembling these prototypes. Each one takes 4 hours of skilled labor. To produce 50,000. Is why I'm sending you to Detroit next week. We're contracting with automobile manufacturers to set up assembly lines. You'll need to train their engineers on your specifications. Eleanor looked back at the testing range, where technicians were already preparing the next firing. From laboratory curiosity to mass production in 6 months. The compressed timeline should have been impossible, but then again, everything about this war seemed impossible until they did it anyway. There's one more thing, Tuve said, his voice dropping. The fuse is now classified beyond top secret. New designation, Project Hush. You will not discuss it outside of APL, not even with other military projects. And most critically, he fixed her with an intense stare. The fuse is never, ever to be fired over land where the enemy might recover an unexploded round. Ocean use only. If the Germans or Japanese get their hands on this technology, they'll copy it, Eleanor finished. Every advantage we have disappears. Exactly. So the Navy loves it, they're fighting over water. But the Army can't use it at all until we're certain every round will detonate. No duds, no captures, no compromises. Eleanor nodded slowly, thinking through the implications. The proximity fuse would revolutionize naval anti-aircraft defense but remain useless for defending cities or ground troops. Unless. What about the V weapons? She asked. Intelligence reports suggest the Germans are developing rocket bombs to attack London. Those would be flying over England, but that's a decision above my pay grade, Tuve said. And above yours. For now, focus on reliability and production. Make me a fuse that can sit in a magazine for 6 months, get fired from a rolling ship in a typhoon, and still kill its target. Then we'll worry about where we can use it. He walked away, leaving Eleanor alone with her triumph and its limitations. She looked up at the empty sky where her test round had exploded and thought about David, her brother, somewhere in the Pacific on a ship that desperately needed this weapon. The Navy would get the proximity fuse first because the Navy fought over deep water where secrecy could be maintained. But what about the soldiers fighting on land? The pilots flying over Europe? The civilians huddling in bomb shelters while V-1 rockets rained down on London? Eleanor made a mental note to keep improving the reliability percentage. Because somewhere out there, beyond the testing range and the classified memos, real people were dying because mathematics was hard and manufacturing was slow and security concerns limited what even genius could accomplish. She turned back to her team. Let's fire another 15 rounds. I want 90% success by end of day. They got back to work. Chapter 5, Camp Edwards, Massachusetts, June 1942. Major Riley stood in the rain, staring at the monstrosity they wanted him to trust. The SCR-584 radar was enormous, a dish antenna 8 feet across, mounted on a rotating platform that looked like it belonged on a battleship. Not a mobile anti-aircraft battery. Next to it squatted a trailer full of electronic equipment that hummed and clicked and occasionally emitted puffs of ozone-scented smoke. And connected to all of it by thick bundles of electrical cables was the M9 Director, a box of black metal roughly the size of a refrigerator, studded with dials, switches, and output connections that led directly to Riley's gun. "Beautiful, isn't she?" asked the civilian in the rain slicker. His name was Harry Murphy, engineer from Bell Telephone Laboratories, and he had the exhausted, manic look of a man who hadn't slept properly in 6 months. The M9 can track a target, calculate the ballistic solution, and direct your guns automatically. All you have to do is load and shoot when it tells you to. Riley's skepticism must have shown on his face because Murphy sighed. "You don't trust it." "I don't trust what I can't see," Riley said. "My gunners have been training for years to track targets visually, to feel the aircraft's movement, to lead the target based on experience. Now you want me to aim where a machine tells me, even if that means pointing at empty sky?" "Especially when it means pointing at empty sky," Murphy corrected. He climbed up onto the gun platform, rain streaming off his slicker. "Major, do you know how many calculations your brain has to perform to lead a target?" "I don't do calculations. I shoot." "Wrong. You do dozens of calculations, you just do them unconsciously. Aircraft speed, altitude, rate of turn, wind drift, projectile ballistic coefficient, Earth's rotation." Murphy ticked them off on his fingers. "Your brain evolved to throw rocks at rabbits, not intercept aircraft traveling 300 miles per hour at 20,000 feet. The M9 was designed for exactly that purpose." Riley looked at his gun crew, huddled under tarps against the rain. Corporal Henderson, his pointer, was watching the exchange with open skepticism. These were good men, experienced men. Men who had practiced their craft through endless drill until their hands moved faster than thought. "Give me a demonstration," Riley said. Murphy's face lit up. "That's why we're here." He called out to the radar operators. "Clarence. Fire up the set. Let's show the Major what we can do." The SCR-584 began to rotate, its dish antenna sweeping the sky. Inside the control trailer, cathode ray tubes glowed to life, showing ghostly green traces. Murphy gestured Riley over to look at one of the screens. "This is your target," Murphy said, pointing to a bright blip on the screen. B-17 bomber, flying at 240 miles per hour, altitude 18,000, range 12 miles. "Watch." The blip crawled across the screen. Numbers appeared beside it, bearing, elevation, range, all updating continuously. And then, incredibly, a second set of numbers appeared, predicted bearing, predicted elevation, predicted range 20 seconds in the future. "The M9 is doing the leading calculation for you," Murphy explained. "It knows where the aircraft is, it knows how fast it's moving, and it computes where it will be when your shell arrives. Feed that data to your guns, and you can't miss." "Theoretically." "Theoretically," Riley repeated. "Well, there are still variables. The target might maneuver. Wind conditions might change. But our test firings show an 8-fold improvement in hit probability compared to optical ranging." 8-fold. Riley looked at his crew again, then back at the humming machines. Everything in his experience, everything he had learned in 20 years of artillery service, told him that machines were tools, not replacements for human skill. A good pointer could sense the rhythm of a target aircraft, could anticipate its turns, could miss. That was the truth he didn't want to face. Human intuition was magnificent for problems humans had evolved to solve. But three-dimensional ballistics at supersonic velocities against targets performing evasive maneuvers? That was a problem for mathematics, not instinct. "All right," Riley said. "Show me how it works. If I'm going to stake my crew's lives on this system, I want to understand every piece of it." Murphy's expression turned serious. "That's going to take a while, Major. I've got time." They spent the next 6 hours in the rain while Murphy walked Riley through the system component by component. The radar sent out pulses of microwave radiation and timed how long they took to bounce back, range. The rotation of the antenna gave bearing. The elevation angle gave altitude. All of that data fed into the M9 director, where an analog computer made of gears, servomotors, and vacuum tubes calculated firing solutions 30 times per second. The gun crews hated, Murphy admitted as they stood beside the M9, watching its internal mechanisms whir and click. They're trained to track targets optically, to use their judgment. Now we're asking them to ignore what their eyes tell them and trust numbers on a dial. Can you blame them? Riley asked. No. But I can prove them wrong. Murphy pulled out a soggy notebook and flipped to a page covered in statistical tables. Last week we ran a comparison test. Best optical fire control team versus M9 director, each engaging the same set of drone targets. The optical team scored 3 hits out of 42 shots, 7%. The M9 scored 26 hits out of 42 shots, 62%. Riley stared at the numbers. That's the future, Murphy said quietly. I know it feels wrong. I know it seems like we're taking the humanity out of warfare, turning your gunners into button pushers. But Major, wars aren't won by feelings. They're won by physics. And the physics say that electronic fire control is superior to human fire control, no matter how skilled the human. The rain was letting up. Riley walked back to his gun and ran his hand along the barrel. He thought about Pearl Harbor, about firing until his gun crew's ears bled while Japanese bombers flew serenely through their barrage. He thought about the pilots who would die if he clung to old methods out of pride. When's the next training exercise? He asked. Tomorrow, if the weather clears. Then tomorrow we'll see if your miracle machine can make believers out of my men, Riley said. He didn't sound convinced, but he didn't sound completely closed off either. That was progress. Murphy smiled slightly. Major, by the end of the week, you'll be aiming at empty sky and loving every minute of it. Riley doubted that. But he was willing to try. Chapter 6, The Pacific Fleet, September 1942. Lieutenant David Vance stood on the aft deck of the USS Mahan, watching the 5-inch gun crew prepare for evening gunnery drill, and tried not to think about how many ways he could die in the next 60 seconds. The new proximity-fused shells had arrived last week in unmarked crates with security classifications that made even the captain nervous. David had attended the briefing where a stone-faced Navy commander explained that the fuses were never to be fired over land, never to be discussed with anyone outside the gunnery department, and absolutely never to be allowed to fall into enemy hands. What do they do? One of the other gunners had asked. They make you better at your job, the commander had replied. That's all you need to know. But David knew more than that because his sister was Eleanor Vance, and while she had never explicitly told him what she was working on, he had put the pieces together from her carefully vague letters. Radio-equipped shells. Proximity detonation. Eleanor's genius, compressed into a metal cylinder and loaded into his gun. Vance. Stop daydreaming. Gunner's Mate First Class Morrison shouted. Target incoming, bearing 270. David snapped to attention and looked where Morrison was pointing. A towed target drone was approaching, pulled by a B-24 bomber at 15,000 feet. Normally they would fire shells with time fuses, set to explode at a predetermined altitude based on estimates of when the shell would reach the target's position. Today they were firing the new ammunition. Load VT fuse. Morrison ordered. The loader, a kid from Ohio named Parker, carefully extracted one of the special rounds from its protective container and slid it into the breech. David noticed Parker's hands were shaking. It's just a shell, David said quietly. It's a shell with a brain, Parker muttered. That's different. The gun elevated and traversed according to the fire control solution from the ship's director. David could see the target drone clearly, a bright orange fabric sleeve streaming behind the bomber. The old David would have calculated, bearing rate, closing velocity, time to target intersection. The new David just watched the gun position itself automatically and waited for the order to fire. Fire! The gun roared. The shell departed at 2,500 feet per second, climbing toward the target at an angle that looked all wrong to David's experienced eye. The shell was going to pass in front of the drone by a good 20 yards. The shell exploded exactly 20 yards in front of the drone, filling the air with shrapnel. The orange target sleeve shredded and fell, trailing smoke. For a moment, nobody moved. Then Morrison started laughing, a slightly hysterical sound. "Did you see that? Did you see that? We didn't even hit it and we killed it." Parker was staring up at the dissipating smoke cloud. The shell knew. It actually knew when to explode. David felt something cold run down his spine. His sister had done this. Eleanor, who used to help him with his algebra homework, who had taught him to see the beauty in mathematics, had created a weapon that made artillery shells intelligent enough to kill on their own. "Reset for second target," Morrison ordered, but his voice was different now. "Odd. Let's see if that was a fluke." It wasn't a fluke. Over the next hour, they fired 15 rounds at various target drones and scored 12 direct kills. The 3 misses were all due to the drone being outside the effective radius when the shell passed. The fuse had worked perfectly every time, the gunnery solution had been slightly off. 12 out of 15. Against optical sighting and time fuses, they might have scored 2 out of 15 if they were lucky. As the sun set and the gun crew secured their station, Morrison pulled David aside. "Your sister works at some kind of lab, right?" David's stomach clenched. "She's a physicist." "Research. Can't talk about it." "That's what I thought." Morrison looked up at the darkening sky where they had obliterated 12 target drones. "Tell her thank you. From all of us. Whatever she's doing, it's going to save lives." David nodded, not trusting himself to speak. He thought about writing Eleanor, trying to explain what it felt like to fire ammunition that was smarter than he was, to watch shells detonate themselves at optimal kill range without human intervention. But he couldn't write that letter because everything about the VT fuse was classified beyond his security clearance. So instead, he went below deck and wrote a simple letter: "Dear Eleanor, I hope your research is going well. The weather here is fine. We had gunnery practice today and the results were extraordinary. I'm proud of you. Love, David." Eleanor would understand what he couldn't say. She always did. That night, David lay in his bunk and listened to the ocean. Somewhere in those dark waters, Japanese submarines were hunting American ships. Somewhere in the sky above, Japanese aircraft were waiting for their chance to bomb and strafe. The war was vast and terrible and close, and human beings were very small. But now humans had weapons that could think. David wasn't sure if that was terrifying or comforting. Probably both. Part 3, The Convergence. Chapter 7, Anzio Beachhead, Italy, January 1944. The sky above Anzio was full of death. Major Riley crouched in the mud beside his battery of 4 90mm anti-aircraft guns, each one now connected by thick cables to the SCR-584 radar and M9 director system. Around him, the beachhead was a nightmare of explosions and machine gun fire as German forces tried to drive the American invasion back into the sea. And somewhere in that chaos, above the smoke and the tracers, German Stukas were diving on the American positions. "Contact," shouted Sergeant Willis from the radar trailer. "Multiple targets, bearing 045, range 8,000, altitude 12,000 and dropping fast." Riley scrambled to the fire control position. The M9 director was already whirring to life, its internal mechanisms calculating solutions faster than any human crew could manage. On the radar scope, he could see 4 distinct blips, descending in the characteristic pattern of dive bombers lining up their attack runs. This was it. This was the moment he had been training for since that miserable day in Massachusetts when Harry Murphy had first tried to convince him to trust the machines. 18 months of drills, of forcing himself to aim where the numbers said rather than where his eyes told him, of watching his experienced gun crews struggle with the same trust issues he felt. "Battery ready," Corporal Henderson reported. The 4 guns were elevated and traversed, pointing at seemingly empty sky 45 degrees away from where the actual German aircraft were visible. Riley took a deep breath. Everything he had learned in 25 years of artillery service told him those gun positions were wrong. The Stukas were diving from the northeast, but the M9 was ordering them to fire northwest, leading the targets by an impossible amount. If the M9 was wrong, if the calculations were off even slightly, they would waste precious ammunition firing at ghosts while real bombs fell on real soldiers. But the numbers from the test ranges didn't lie. 62% hit probability versus 7%. Physics versus instinct. Mathematics versus experience. "Fire mission," Riley ordered. His voice came out steady. "Commence firing." The 4 guns opened up in sequence, 1 round every 3 seconds per gun. Riley watched the shells arc away from the battery, climbing toward the intercept point the M9 had calculated. The shells were still climbing when the first Stuka entered the kill zone. The anti-aircraft shell exploded 25 yards from the Stuka's wing. The aircraft shuddered, fragments tearing through its control surfaces, and began to spiral downward trailing black smoke. "Retry continue hit." Willis screamed from the radar trailer. "Target 1 destroyed." But Riley barely heard him. He was watching the second and third Stukas enter the kill zone, watching the M9 automatically adjust its calculations to account for their evasive maneuvers, watching shells detonate in precise patterns around the diving bombers. The second Stuka took a direct hit from a proximity-fused shell. The aircraft simply disintegrated, transformed from a deadly weapons platform into falling debris in the span of a heartbeat. The third Stuka pulled out of its dive, releasing its bombs early to escape the kill zone. The bombs fell harmlessly into the surf 200 yards from the beach. The fourth Stuka never made it to its attack run. 3 shells bracketed it in quick succession, and the aircraft's fuel tank exploded in a orange fireball. 4 targets. 3 destroyed, 1 driven off. Total engagement time, 42 seconds. Total rounds expended, 28. Riley stood frozen, his ears ringing from the gunfire, his mind struggling to process what he had just witnessed. In his entire career, he had never seen aerial targets engaged with such brutal efficiency. The M9 director had tracked the Stukas through their dives, calculated their future positions faster than they could change course, and directed his guns to fire at empty sky that would, milliseconds later, be filled with enemy aircraft. "Major." Henderson was beside him, his face split by an enormous grin. "We got them. We actually got them." More contacts were appearing on the radar screen. The Luftwaffe wasn't giving up, more aircraft were inbound, probably drawn by the smoke from the destroyed Stukas. Riley felt something shift in his chest, some last resistance finally breaking. He had spent 18 months fighting the M9 director, resenting its intrusion into his craft, mourning the obsolescence of human skill. But standing here in the mud of Anzio, watching his battery engage targets with superhuman precision, Riley finally understood what Harry Murphy had been trying to tell him back in the rain at Camp Edwards. This wasn't about replacing human skill. It was about augmenting it. The M9 didn't make gunners obsolete, it made them deadly. "Battery!" Riley shouted. "Engage new contacts as they appear. Fire for effect." The next wave of German aircraft approached the beachhead and met a wall of exploding steel. The M9 director tracked each target, calculated each solution, directed each gun with machine precision. Riley's crew fell into a rhythm, load, fire, trusting the director to guide their aim, trusting the mathematics to deliver death to the right coordinates at the right time. By the time the German attack broke off, Riley's battery had fired 147 rounds and scored 11 confirmed kills. 11 aircraft destroyed, more than his entire battalion had achieved in the first year of the war combined. As the guns cooled and the crew reloaded, Harry Murphy emerged from the M9 trailer. The engineer looked like he had aged 10 years in the last hour, his face pale and his hands shaking. But he was smiling. "Major Riley," Murphy said quietly. "Do you believe now?" Riley looked at his guns, at his crew, at the smoke trails from 11 German aircraft falling into the Mediterranean. He thought about Pearl Harbor, about firing until his arms ached while Japanese bombers flew untouched through his barrage. He thought about Corporal Henderson asking, "What do we do? How do we stop them next time?" Now he knew. "I believe," Riley said. "God help me, I believe." Murphy nodded slowly. "Good. Because the real test is still coming. We've got reports of something new, German rocket bombs called V1s. Faster than anything we've engaged before. If those start hitting London." He didn't finish the sentence. Riley understood. The V1 buzz bomb was a pilotless aircraft, a robot weapon that flew straight and level at 400 miles per hour. Against conventional fire control, it would be almost impossible to intercept. But with the M9 Director and the SCR-584 radar. "When do we deploy to England?" Riley asked. 2 weeks, if we can get the equipment shipped. You and your battery are being transferred to RAF Fighter Command. Special assignment, defending London. Riley looked at his crew again. Henderson was laughing with the other gunners, recounting the engagement, probably exaggerating the size of the explosions. These men had trusted Riley, and Riley had trusted the machines, and together they had achieved something impossible. "We'll be ready," Riley said. That night, as Riley sat in his tent writing his after-action report, he found himself describing the M9 Director in terms he never thought he would use: elegant, precise, beautiful. There was a section in the report where he was supposed to note any difficulties or concerns with the new equipment. Riley left it blank. The only concern he had was that they hadn't deployed these systems sooner. Chapter 8, Applied Physics Laboratory, March 1944. Eleanor stood in the corner of the laboratory, watching a VT fuse fail, and tried not to scream. The test shell had been stored in a climate chamber at -40 degrees Fahrenheit for 2 weeks, then brought to room temperature and subjected to standard vibration testing. The fuse had transmitted its signal properly for the first 30 seconds, then abruptly stopped. When the technicians opened the casing, they found corrosion on the battery terminals, invisible microfractures in the protective coating that had allowed moisture to seep in and slowly oxidize the connections. It was the 14th failure in the last month. The VT fuse worked perfectly under laboratory conditions and worked perfectly in naval combat over the ocean. But field reports from North Africa and Italy were showing a pattern of duds, shells that failed to detonate because the fuse had degraded during storage in extreme conditions. Dr. Vance? Her assistant, a young physicist named Robert Chen, approached cautiously. "The production liaison from Western Electric is here. He wants to know if we're approving the next batch for manufacture." Eleanor closed her eyes. Western Electric was producing VT fuses at a rate of 40,000 per month now, a staggering achievement of mass production. But they were manufacturing to specifications Eleanor had finalized 18 months ago, before anyone understood the environmental stress factors that real combat introduced.